welcome to this video in the nuclear chemistry unit. This is 18.2, where today we're going to teach you how to differentiate between the different transmutation types and write your own balanced nuclear equations using the emissions that are on table O and introduce to you table N in the New York State chemistry reference tables. If you haven't already done so, make sure that you have printed out and have handy your companion worksheet, and you're also going to need your CSERT and periodic table. So without any further ado, let's get cooking. The first part of this video is going to delve into the differences between the different transmutation types. Radioactive decay will fall under two categories. That is what we call natural transmutation, which we did allude to in our first video, and artificial transmutation. Let's get into natural transmutation first. Natural transmutation is what you have been doing all along with your radioactive emissions. It is a spontaneous process, and the nucleus is decaying on its own. Why? Because that neutron to proton ratio is upset, and the radioactivity is happening so that radioactive particle can get back down to a stable neutron to proton ratio. I can tell we have natural transmutation by looking at a decay equation, and the big secret for me is what you see here in red. I usually see one reactant, which is your radioactive isotope, and two products that are present, one of which is usually your table O emission, and the other is your daughter isotope, whatever the original parent isotope turned into after it lost the emission from table O. So as we can see in all of these, we have one reactant and then two products present. Occasionally you may have more than two products here, but the one reactant that's here tells me this process is spontaneous. Artificial transmutation is going to look a little bit different than natural transmutation. First of all, artificial transmutation is caused by externally stimulating an atom. Essentially, a scientist is going to bombard a nucleus with a particle, and that's done via a particle accelerator, which we see here at the bottom. The particle that's now accelerated lodges itself in the nucleus, and if it sticks there, it essentially is going to change the number of protons that is in that atom's nucleus, and thus change the identity of the atom. That is how many of the man-made atoms that sit at the bottom of your periodic table were created. Telling the difference between natural and artificial transmutation is tough. So here we see what we wrote before about natural transmutation, whereas now the first thing we'll point out in artificial transmutation is that, yes, we are forcing decay to happen. Well, how is that occurring? Well, we are bombarding a nucleus here with an existing particle. So the first thing I'm seeing is that where in natural transmutation I saw only one reactant, in artificial I am now seeing two. And those reactants are usually an alpha particle or a neutron. You can't really go by what you see on the product side because, as we saw before, we see two products here in natural transmutation, we see two here in artificial, and sometimes you might even have three. But the idea is compare what you see in the reactants to tell the difference. It requires, when you have an artificial transmutation, the bombardment of an existing particle by something else, and this is the something else here. So this is a non-spontaneous process where the decay is forced to happen by that accelerated particle. Okay, now it's your turn. Let's analyze the following reactions here on the right-hand side and circle each that you would consider artificial transmutation. Pause the video now and then unpause it when you're ready for the answer. All right, if you did it correctly, we should have had 4 of these reactions being considered artificial and 2 of them being natural transmutation. Remember, we are looking at the number of reactants that are here, with artificial having 2 and natural only having 1. Now we are ready for part 2 of this video, where you are going to learn how to write your own decay equations. So let's start off by teaching you guys how to do this, and it's pretty simple because we're going to use a lot of the skills that we picked up in lesson 18.1. So go back and check that out if you need to. So in order to effectively do this, one of the things that you have to do is read, and we know sometimes that can be a struggle. But let's make sure we can decode the question. Our first example says write an equation that shows the decay of polonium-210 by alpha emission. So this is saying the decay of polonium-210. That means I'm starting with polonium-210. So I know the symbol for polonium is PO. The mass number is 210. I've got to go look up the atomic number on the periodic table, and I see that it's 84. And I see the question is telling me that we are undergoing an alpha emission. I know an alpha emission is a 4,2 alpha particle. So this is going to be spontaneously happening. I am now going to put the alpha particle in here. And now I must have conservation of mass and charge. If I have 210 on this side and I have 4 plus what gives me 210? Well, all you mathletes out there know it is 206. And now I have to have conservation of charge here on the bottom. 84 here. 2 plus what gives you 84? It's 82. Now comes the time we look into our periodic table and we say, what has an atomic number of 82? You got it. It is lead. So we just effectively wrote our first decay equation. This one is a little more difficult. Here it says boron 11 is formed by electron capture. Okay, so we haven't really talked about what electron capture is, but in parentheses you can see here it says electron absorption. Electron capture is essentially when an electron, which we see over here, is bombarded at a nucleus. And what that high energy electron does is effectively change the atomic number without changing the atomic mass that's up here. So the iodine 125 becomes tellurium 125. And this is not a spontaneous process. Electron capture is a non-spontaneous process. So now let's see if we can solve this equation. It says B11 is formed. That means that I am making B11. It's in my product. So I actually will work backwards in this. And I'm going to say, all right, I'm going to make boron 11 as a result of this. I go to my periodic table and I see boron's atomic number is a 5. We are going to figure on that being formed by an electron capture. So that's my table O emission that I'm putting there. I'm going to put it with an E to represent that it's an electron. And now we have to have conservation of mass and charge. Because an electron has virtually no mass, and it's listed here as 0, our mass number for whatever this is going to be here is an 11. Now I got to have conservation of charge. 5 is here. Something, x minus 1 equals 5. Well, you could do a little mental algebra and see that that answer here would be 6. Now I go to my periodic table and I say, what has an atomic number of 6? You guessed it. It is carbon. So here we see that carbon 11 is being bombarded or capturing or absorbing an electron, and it is now turning into boron 11. Now it is your turn. You guys get a chance to try and write decay equations. Make sure you read and decode, and then make sure you have conservation of both mass and charge. Pause the video now and then unpause when you're ready for the answer. All right, if you did this correctly, here is what you should have gotten. Not too bad. The only thing that I think could have caused you some trouble was understanding whether you are absorbing or you are emitting. And we can see in this first example that is here, we had an emission, so this is a spontaneous process right there. This second example was again an electron capture or an absorption, so I had to put my decay product in my reactant. And this one was the funkiest of them all, where it said you have alpha absorption by a nitrogen 14. So I had my alpha particle here, and of course we formed something new. In this case it was a fluorine 17, but out with that fluorine 17 did come a neutron. So make sure that you read carefully as you're doing these problems so you don't get them wrong. Part 3 of this video is going to be continuing our work with decay equations, but now we are going to introduce to you guys CCERT Table N. So grab that chemistry reference table and open that up to Table N. You guys will see that Table N is a table that we have not used this year yet. What Table N is going to be used for in the short term right now is helping you to predict the type of decay mode that any of these radionuclides are going to undergo at any given time. Additionally, it'll also tell us the half-life, but we're not going to worry about that yet. That's in a subsequent lesson. If we look closer at this, the way we interpret this table is pretty simple. It says gold 198. Well, if we wanted to write a decay equation for the spontaneous decay of gold 198, we'd have to know what kind of decay mode it underwent. Well, surprise, that's where table N comes in super handy. It's telling me that the primary type of decay that gold 98 undergoes is a beta decay. Carbon-14 undergoes beta also, calcium-37 undergoes positron, and cobalt-60 undergoes beta emission. All right, let's dive in and practice our first problem utilizing table N. We are going to write the decay expression for carbon-14. Now, you'll notice that this is different because they did not tell you the type of decay it undergoes. This is where we go right to the table now. We find carbon-14, which is here, and we see it undergoes a beta decay. So we are going to start with our nuclide that is radioactive, that is carbon-14, and I'm going to go to the periodic table and put in the atomic number so I have it. It's going to go beta decay, so that's a beta or an electron minus 1. And we have to have conservation of mass and charge, 14 on this left side. 0 plus what is 14? You guessed it, it's 14. And now we got to have conservation of charge. Something minus 1 gives me 6. That would be 7. I go to the periodic table and I say, what element has an atomic number of 7? It is nitrogen. So here is the decay expression for carbon-14. Now it's your turn. Pause the video now and write the decay equations for any of the radionuclides that you are given in the question. Unpause when you are ready for the answers. All right, if you did this correctly, here is what you should have gotten. This is pretty straightforward and is not going to be too bad. You just have to make correct use out of table N. So that is it for us. If there is anything in this video that you found perplexing, make sure you bring your questions to the Burning Questions segment tomorrow. Once again, it has been a pleasure guiding you through the myriad of topics here in the Nuclear Chem chapter. I will see you on the flip side. Peace out!
That's all, folks.